Hi, today I want to share you with the rule by which the effective number is determined and the data is overflowed. And let's see the example case in C. And I have got number one, it's a number storing 50,000, and number two, it's assigned 50,000. And if you do the multiplication of these two numbers and store it to data stored in int, then the data has overflowed and it gives negative number. And let's see the result by running the program, and you can see that it will give this number. And actually, if you do the multiplication of these two numbers, as you all know, that the number it should give is this 50,000 times 50,000, and see the the number should have been this. But actually, whether the data is overflowed or it has not. The underlying bit representations do not change. And I'll let's I'll here we learn the rule that determines the effective number when the data has overflowed. So let's turn it to unsigned, and let's print out the number in binary form. The binary form of the result of the multiplication of these two numbers. And I've got let's call the function here, and you can see the binary form of the number, this one, the 2.5 billion. And I've already written it down here, and you can check whether it matches this number. And I've put that down in reverse order. Put this binary numbers in reverse order down here, because it's easier to use this column number as for calculating the power of 2 for the correspond for the pointed bit, unless you wanna calculate it by yourself. And in the case of unsigned, you the most significant bit is used as positive number, and if it's two's complement, as we'll see later, the most significant bit gives the negative number. And let's go to see if the let's see whether this bit representation gives this number by turning it to decimal number. Uh, let's go to calculate it, and you see this bit matches this one. So if you see the column number, it's 32, and the it should be 2 to the 31, because you know the rule for turning the binary numbers into decimal number. The power is determined by the position of the current bit minus 1. And let's keep going. The column number is 29. 2 to the 29. 2 to the should be 2 to the 28. 2 to the 28 plus 2 to the 26. 2 to the 26 plus 2 to the 24, 2 to the 24, and 2 to the 17, 2 to the 17, 2 to the 15, plus 2 to the 15, plus down to 2 to the 11, 2 to the 14, plus 2 to the 13, plus 2 to the 12, plus 2 to the 11, plus the next meaningful bit is gives column number 9, and plus 2 to the 8. Yeah, actually, you can see that it matches the earlier number, 2.5 billion. And let's calculate it by applying 2's complement rule. So let's go and see to the, because now it's 2's complement. The most significant bit should give negative number, and you apply minus 2 to the 31 plus 2 to the 28, 2 to the 28 plus 2 to the 26, 2 to the 26 plus 2 to the 24, 2 to the 24 plus 2 to the 17, 2 to the 17, 2 to the 17 plus 2 to the 15, 2 to the 15 plus down to 2 to the 11, 2 to the 14 plus 2 to the 13, 2 to the 12, 2 to the 11 plus 2 to the 8, 2 to the 8. And you can see that it gives this number, and let's see, by changing the time which follows 2's complement into type, and change these types as well, and then see the result, and you see that this number matches this number we have just calculated. And let's see the case of unsigned. Let's turn it to unsigned and change this as well. And change the directive because we wanna print out unsigned. And you can see that this gives the correct number, and you can see that whether it gives this number by 2's complement or unsigned, the underlying representations stay the same, and we have just seen by calculating the number by applying either by unsigned and 2's complement. And I wanna finish off here, and thanks for listening. Bye.